Let me introduce Dr. Jill Tarter, who is the director of the Center of SETI, which stands for Search for Extraterrestrial Intelligence. That's really very exciting. And also she's a Bernard Oliver, sorry, I said it in French, Oliver, chair of SETI. Dr. Tarter earned a bachelor in physics with distinction at Cornell University and a master's degree and a PhD in astronomy from UC Berkeley. She served as a lead scientist in NASA SETI program, the High Resolution Microwave Survey, from 1993 to 1999. Dr. Tarter led Project Phoenix, a survey of radio signal from about 800 nearby star systems. She is currently on the management board for the Allen Telescope Array, a joint project between SETI Institute and UC Berkeley Radio Astronomy Laboratory. And let's welcome Dr. Jill Tarter.
Actually, I want to say that my first degree was in engineering physics. Yeah. So I'm gonna actually show you some hardware and technology and gear more than otherwise, because I really like that stuff. And I'm really delighted to be here today. So where's here, right? This is where you probably think you are, but I'd like to expand your perspective, right? The news that's coming out of Japan and the Mideast revolutions and the really growing concern about climate change remind us that we all live here, right? And when the Cassini spacecraft was at Saturn, it looked through the rings and it imaged us here. And the Voyager 1 spacecraft in 1990, as it was going past Neptune and going out of the solar system, looked homeward and it saw us here. We're here, and ultimately, we're here, right? It's all about perspective. Perspective can change. Perspective can be changed. I'm trying to do that. Give you a more cosmic look at things. And my explanation of this image is that we live in a fragile island of life within a universe of possibilities. Now, one of the possibilities that we've wondered about for a long time is planets orbiting other stars. And one way to detect planets around other stars is to notice the effect of on the star of the planet going around it. It tugs the star just a little bit. So we measure the motion of the star back and forth on the sky and forward and back with radio velocity. But we've now got another way to find planets around stars. This is a spacecraft called Kepler. It was launched in March of 2009. And its job is to find small Earth-sized planets orbiting other stars. The radio velocity and astrometric and gravitational microlensing methods find big planets. We want to find an Earth-sized planet around nearby stars. And so Kepler was 25 years in the making before it launched. And its job is to look for transits to find these small Earth-like planets. Occasionally, a planet's orbit will align just the right way so that it passes in front of its star. And Kepler's very, very precise movie cameras can measure the dip in the light from the star while that transit is taking place over several hours. And then the next time the planet comes around, you see that dip again. And now you say, oh, now that's a period of a planet. You can predict when it's going to happen the third time. And so Kepler requires at least 3 transits to detect a planet. And this animation makes Kepler's job look easy, all right? You just look for that big drop in brightness. Well, this is an animation, right? Kepler One of the reasons it took 25 years to get that spacecraft launched was we couldn't convince anyone that we could build precise enough instruments, things that would measure the intensity of starlight, to a few parts in a million. Right? It has to be in space. The atmosphere messes up observations from the ground. Why do we need that? Well, if Jupiter passes in front of a star like the Sun, it dims the star's light by 1%, a part in 100. That's an easy measurement. You can do that from the ground. But a planet like the Earth dims the light by only a part in 100,000. So our precision has to be parts per million. And Kepler can do that. So, not all planets and all stars will line up appropriately. So if Kepler's going to find planets by transit methods, it needs to look where there are a lot of stars all in one area of the sky. So this is actually an astronomy picture of the day. It's a digital image taken in Northern California. If any of you are from there, you can see Mount Shasta on the right and Lassen on the left. And I love this image because our observatory is right up there next to Mount Lassen. So this is the Milky Way. You look up in the summer sky, and that band of light going across the sky is stars, lots of stars. So here you see a picture with a large telescope of, again, a particular area of the Milky Way. And between the constellations of Cygnus and Lyra, Kepler is staring at an area that's 100 square degrees on the sky. Well, how big is that? Hold up your hand at arm's length. That's how much of the sky Kepler is staring at. We actually moved that area up off the actual plane of the Milky Way itself because there would have been too many stars in that 100 square degrees, and Kepler would have been confused. Each of those 42 rectangles is an array of CCD devices, extremely precise, thin CCDs, right? So Kepler works just like your cell phone camera, except that instead of having 3 megapixels or 10 megapixels, Kepler has 95,617,600 pixels. And when we ejected the lens cover a couple of days after launch, this was the image we saw. Actually, I'm now going to show you the negative of that. I was afraid this might not project very well. Okay, this was the image we saw. There are 4.5 million stars above the threshold of intensity in this field of view. To give you a better idea, let's blow up the center rectangle. That's the kind of star field. Each one of those dots is a star. So of these 4.5 million stars, Kepler is staring constantly at 165,000 of these stars, taking a measure of the brightness of the star every half hour, day and night, day after day. And as of February 1st of this year, we know that 1,235 of those stars are actually winking at us. We're seeing the drop of intensity. These are 1,235 candidate exoplanets, and they're color-coded for their size. There are 184 of these that are Jupiter size or bigger, 662 around the size of Neptune. There are 288 super-Earths, the kind of planet we actually don't have in our own solar system, right? And there are 68 of these that are Earth-size. Now, we've only had 2 quarters of data that have been released to the public that these detections are based on. That means to get 3 transits, we're talking about things that have periods shorter than about 25 days. So all these planets are close to their stars. And as the Kepler mission goes on, we can expect to be finding planets that are farther and farther away until we get to, we hope, an Earth-sized planet at the distance that the Earth is from the Sun, with a period of about a year. All right? Now, another way to look at this wonderful richness of planets is this. There are actually 1,235 black spots here. The circles are the size of the stellar disk, from the biggest stars up on the upper left to the tiniest star down on the lower right. And for comparison, that's us. That's the sun, its size. So we've got planets, stars that are much bigger than the sun and much smaller than the sun. And you see a black spot there, but you have to increase the image, because that black spot is Jupiter. But you can, in fact, find the Earth in a big enough image. So that's the comparison. That's what Kepler is trying to find. And we can calculate that 54 of these 1,235 planets are at the right distance from their star, so that they might have liquid water on their surface, what we call the habitable zone. You can imagine it's Goldilocks story, you know, not too hot, not too cold. Liquid water might be the key to life, at least life as we know it, and so it's one of the things we're really eager to find out there. Now, when we were thinking about planets around other stars, we had this picture of our solar system. All the planets in a plane, they have very circular orbits. The little guys are inside, the big guys are outside. And the laws, Kepler's laws that tell us about how these planets orbit, are so simple that we talked ourselves into expecting that when we found other planetary systems, they'd be just like ours. Wrong. And it's a problem with science when you have only one example. You can convince yourself that everything is like that. The most wonderful thing about extrasolar planets is they've shown us the variety in the universe. The first planet we found, more massive than Jupiter, it went around its star in 4 days. It was essentially touching the star. It was so close. So Kepler's laws work out there, but the variety of planetary systems that we've discovered is just stunning. We're learning so much about systems. We now know that giant planets, when you make them, they don't stay where they're born. They migrate in close to their stars in some of other systems. Some of them have already been consumed by their stars. Some other planets, it's a big billiards game out there, and they get thrown out of the planetary system. And look at these amazing, they're just amazing orbits here. There's so much to be learned. And it just really does bring home the fact that it's very hard to predict the universe of possibilities out there with an example of just one. But now we have an example of at least 1,235. And some of them are really weird systems. This is one of my favorites. This is Kepler 11. There are 6 planets in this system so far. There may be more planets farther out that we haven't found. But look at the geometry of this. It's really pretty amazing. There are 5 planets all inside the orbit of Mercury, and one more out before you get to an orbital distance of Venus. And those planets interact with one another. We can see how a planet coming past another planet retards or advances its traverse around its orbit. We can see the interaction of those inner 5 planets. That's how precise our measurements are. It's really cool. Believe me, it's really cool. So, Kepler looks at 1/400th of the sky, and the Kepler field is very far away, about 1,800 light years. A light year is 6 billion miles. It's the distance that light travels in a year. So those are far away, only a patch of the sky. So we can use that to do statistics and predict that there are at least 50 billion planets in the Milky Way galaxy that we live in. And probably 500 million of those could be habitable with liquid water. So now is the perfect time to ask this question that we've been asking for a long time. For millennia, we asked the priests and the philosophers, what should we believe? Is there life out there? Okay, now Now Kepler's shown us planets, and we have technology in the 21st century that can try and answer that question by doing an experiment rather than asking someone what to believe. So it's a really exciting time for SETI. Now, we've been doing SETI for a while.
Imagine refuge. In order to figure out if there are fish in the ocean, you dip an empty glass into the water and look inside. No fish in the glass? Well, there must be no fish in the ocean. Not too logical, is it?
No, not too logical. But that's where we are with SETI. We've been doing it for 50 years, but relative to the cosmic ocean, what we've done in that 50 years is sample one glass out of that ocean. So it's much too early to be making claims like Paul Davies' eerie silence, if any of you have read that book that came out last year. We don't know. We need to build bigger glasses that dip the ocean faster. And we don't know the extent of life. We don't know whether it's possible for life beyond our own planet. So I have lots of colleagues at the SETI Institute who are working in a field called astrobiology. They're trying to figure out what biosignatures they could detect remotely once we begin to find planets like the Earth around nearby stars. And they want to be able to say, okay, the atmosphere of that planet has particular characteristics that probably mean there's biology there. But if we find those biosignatures, we won't know whether they're just microbes or maybe there's some mathematicians, maybe there's some engineers there. And so SETI is trying to look for technosignatures, right? Not just life, we're trying to find technology, evidence of someone else's technology. So our own technology in the electromagnetic spectrum is visible over interstellar distances. There are things that we generate, signals that we generate. Well, their technology might be as well. They might be generating signals in the optical or the radio for who knows what reasons, maybe a big communications network, maybe a shield against asteroidal impacts, a big radar, who knows? But if we do a determined search at optical and radio wavelengths, perhaps we can find evidence of that technology. And that's really what SETI is. Now, what's going to determine whether SETI succeeds or not is the mean distance between technologies within our galaxy. And you have to remember that's distance in space and distance in time. Right? So the longevity of a technology is key to the success of a SETI enterprise. Right? If technologies develop over the 10 billion year history of our galaxy, and they pop up and they last for 100 years, you know, that's basically the age of our technology. If that's as long as it lasts, there are never going to be any two technological civilizations close enough in space and in time to discover one another. That's why Phil Morrison, professor at MIT, likes to call SETI the archaeology of the future. Now, light travels at a finite speed, so if we get a message, a signal from someone, we're going to learn about their past. That's the archaeology bit. But the future, it's our future we can learn about, because a successful detection will tell us that technology can persist for a very long time. It's possible to have a future. And we're such a young technology, we don't have any other way of knowing whether we're going to persist or whether we're going to do ourselves in. So, SETI is the archaeology of the future. That's what gets me up every morning and working on this project. And so we're using the tools of the astronomer in the 21st century. We're building new tools to make bigger glasses to explore the cosmic ocean, faster glasses. And this is the tool that we've been working on for the last decade. It's called the Allen Telescope Array because Paul Allen funded the technology development, and the first phase of construction, and this is the telescope that's been built up near Northern California. It's an array of telescopes. It's a large number of small dishes hooked together with a whole lot of computing. So now suddenly silicon is as important as aluminum and steel in this device. And we can make progress and improve our array both by building more telescopes for more collecting area and improving our computing processing at the back end. Now, I told you I was going to show you gear because I love this stuff, and I suspect most of you have no idea what a radio telescope is, much less what an array of radio telescopes is. So I think I put in a tutorial. Okay? We have 42 today. We want to grow this to 350 telescopes in the Hack Creek Valley. All right? So what does a radio telescope do? Well, it has a parabolic surface, which means that it focuses the incoming radio waves, or if this were an optical telescope, the light rays that are coming in, it focuses them all to a point. And you see information about one point on the sky. You can, with a radio telescope, have another receiver close to it to see another piece on the sky. Right? In fact, if you want to build the equivalent of a camera, you can try to have a, I have to stand over here, a focal plane of receivers. But you can see those physical receivers, there's gaps, and you can imagine the image of the sky they make isn't terribly pretty. So we're trying to build digital phased arrays for the focal plane of our radio telescope to get images of a bigger piece of sky. But that was just a single dish. All right? When we build big single dishes, we have to build them out of small panels of reflecting material. This is the Green Bank telescope, which was completed a couple of years ago. It's 100 meters across. Right? And you can see that that surface is made out of individual panels. So now let's take that a little bit farther, and let's break up our big dish into panels. And let's curve each of those panels into an individual telescope. So now the radiation comes in from free space. It's picked up by each of those telescopes, and it's focused, right, to the focal point of each of those small parabolas. So now you have to get some cable. You have to have detectors at the focus of each of those telescopes, and you have to bring the voltage as a function of time on cables, and you arrange the length of the cables so that they would go to the same focal point that you had before. That what you're doing here is arranging that the signals from the sky all travel the same distance. So when you get to a telescope or a panel at the edge of the dish, okay, it's had a shorter path length than one down here, so your cable length needs to be longer. You bring the voltages together and you square them to get intensity, right? And of course, nobody's hanging cables up in the sky, right? You put the cables down on the ground, but you manage to keep the length of them correct so that the signals travel the same path length, the same amount of time. And of course, you don't have to have the antennas on a curve. Put them on the ground. Use the ground as a support system, but make sure the cable lengths are right. Okay? Now, when you have a single dish, it looks at a field of view on the sky and has a spatial resolution that's set by the diameter of the dish. There's a degeneracy there. You see one field of view, and that's your spatial resolution. When you have an array of dishes, the field of view is still set by the diameter of the dish. We're using little dishes. We've got a big field of view. But the spatial resolution now gets determined by how far apart you put these telescopes on the ground. If you put them farther apart, you're essentially simulating a telescope with a diameter that's that big out of telescopes that's diameters are small. So that's what an array does. And of course, you can do this with one set of delays, and that gives you the image of a point on the sky. When you add these all up and phase them, you can have another set of delays that gives you the image of another point on the sky. And you can imagine doing that. Oh, and by the way, we don't use cables anymore. We used to. We actually used to have delay cables, and you clicked in different lengths of the physical analog cable to do this delay trick. Of course, now it's all done digitally, right? So we get rid of those cables, and we'll just use some bits here. All right. Now imagine doing this trick of different delays many, many, many times. So addition becomes multiplication. A massive addition becomes a multiplication. And what you're doing is you're multiplying the voltages from each from each pair of telescopes together and then correlating them. All right? So what we're doing is forming a spectral imaging correlator. And for those of you who like the math, we're forming a visibility function on the ground based on the brightness temperature of an image on the sky. Right? So our dishes look really funny. They're what's called offset Gregorian feeds to keep the noise, the interference that are coming. Every telescope has peripheral vision. Every telescope has side lobes. But this telescope has very low side lobes. We want to work over a large range of frequencies. So when we put a secondary reflector here, it has to be at least 5 wavelengths across for your lowest frequency. That makes it big. If you put it in the center of the dish, it would block most of your collecting area. So we put it down here. And we put this green shield, which is a metal cover, to keep this, which is the feed and the receiver, from seeing the ground, which is at 300 Kelvin and radiates like a black body and is noise. And then we put this radome cover, which is a fancy kind of canvas over it, to keep out the rain and the snow and the birds that want to build nests in our system. And here's how the optics work. The radio waves come in from the sky. They bounce off the primary, they bounce off the secondary, and they get focused onto this feed. It's a log periodic, extremely wideband feed. It receives all frequencies from 0.5 gigahertz, that's 500 megahertz, to 10 gigahertz. So that's a 20-to-1 frequency range. It's a frequency-independent log periodic feed, very, very unique to this telescope. And I showed you an artist's conception of what the telescope looks like in the Hat Creek Valley. You've actually already seen the explanation for why those dots really aren't random. You saw it in the math. Okay, so our telescope will, when it has 350 dishes, have the spatial resolution of a telescope that's 900 meters across, our longest baseline. And if you imagine the vector that connects any pair of antennas, the vector has a direction and azimuth, north, east, south, and west, and it has a length. So we arrange the pattern on the ground of the antennas so that the azimuthal coverage is uniform. We have as much sensitivity in that direction as we do in that direction. And we arrange the spacing, the length of the vector, to match a Gaussian as closely as we possibly can. And why do we do that? Because the Fourier transform of a Gaussian is a Gaussian, and that's your beam on the sky. So when you only have 42 telescopes, this is kind of the beam with which we look on the sky. 98, that beam gets better looking. 206, better still. By the time you have 350 telescopes, you have a beautiful point spread function. You have a beautiful symmetric beam on the sky that samples all spatial scales equally. All right, so what does this mean for you, the consumer, right? Let's look at something that's nearby on the sky. That's our nearest neighbor galaxy, M31. The moon is down there for comparison. The moon's 0.5 degree across. M31 is 2.5 degrees across. Now, our largest radio telescope is in Arecibo, Puerto Rico. It's 1,000 feet across, 300 meters. That's how much of the sky it sees, right? Big telescope sees only a little bit of the sky. Little telescope sees a lot. All right? I talked about focal plane array receivers. Well, Arecibo's now put in 7 receivers in a focal plane array to try and expand how much of the sky they see at once. Because, by the way, if you wanted to make an image of that galaxy using Arecibo, you're going to have to point it thousands of different times to image that galaxy. But with the small telescopes in the Allen telescope array at L-band, at 1.5 gigahertz, that's our field of view. 2.5 degrees all at once, with a spatial resolution that's better than this, because our telescope is 900 meters across by the time that we get to 350, and right now 300 meters across, so the spatial resolution is comparable. So we can make a picture of the sky. We talked about Kepler's CCD. Well, we don't have 95 million pixels, but we have about 18,000 different pixels independent on the sky, and each one has 1,024 spectral channels or colors. It can break the incoming radiation up into that many channels. And with, so it's a wide-angle radio camera. There's never been one before. And with 61,075 n-1/2 baselines from pairs of antennas, we can make a snapshot. It's point and shoot. We don't have to take data for a long time and let the Earth rotate to change our baselines, or pick up our telescopes on one day and move them to a different baseline the way they do at the Very Large Array in New Mexico. We've got all those baselines, that beautiful beam on the sky. It's point and shoot snapshots. First time it's ever been done. And in addition to doing the correlation, making the image, we can add up the voltages rather than multiply them, and we can pick out right now 3 individual pixels anywhere in that field of view. Well, what does that do for you? Oh, and here's something else. When we do the math to add up the beams, we can also add them up in a way that isn't quite perfect. So this is the main beam of the blue curve of our perfect addition. If we tweak the coefficients with which we add these beams together just a little bit, we can get that red curve. So now it's not quite as sensitive in the direction we're pointing, so the red curve's below the peak of the blue curve. But look what happens over here. You get a null. You get a place on the sky where there's no sensitivity. So you can put a beam and you can put an offset null. And you can do a great deal with that in terms of looking at SETI sources and trying to rule out interference. So here's our friend M31 again, an optical picture. What do you see? What's the brightest thing in this picture? It's the stuff in the center, the stars that are bright and have a lot of ionizing radiation around them. Okay, let's make a picture of this galaxy in the emission line of neutral hydrogen with the Allen telescope array. Looks completely different. There's nothing in the center. That's because that radiation, that ionizing radiation, is turning the neutral hydrogen into ionized hydrogen. So there's no neutral gas there. And the intensities around the ring show you where the hydrogen is located. So that's done with a correlator by my radio astronomy colleagues. And while they're making that kind of an image, I have a catalog of 250,000 stars in our Milky Way galaxy that I want to look at, I want to listen to for signals from someone else's technology. And so wherever my radio astronomy colleagues are looking, I have these stars that project on that same field of view within our galaxy, and I can do that beam forming trick. And I could take these 3 beams and I could place them on this star or that star or that star, 3 at a time. And I can put the outputs from those beamformers into spectrometers that have hundreds of millions of channels to look for narrowband radio signals from a technology. And also, we're looking at 20 square degrees. Remember I showed you the picture of the plane of the Milky Way galaxy? Well, I've broken that up into about 3,000 cells. And 3 beams at a time, I'm surveying that part of the Milky Way. Why? because along those lines of sight, just like the Kepler, looking for a lot of stars in one region, along those lines of sight to the 20 square degrees that I'm surveying, there are somewhere between 4 and 10 billion stars. So I look at nearby stars for faint signals. I look in this region where the most stars are and wonder, are there any really strong transmitters out there? Because these are far away. And for a transmitter to be detectable by our hardware, if it's at the distance of the center of the Milky Way, that transmitter has to be 20,000 times stronger than the current Earth's strongest transmitter. But we don't know that there aren't technologies out there that can do this. So we look where there are a lot of stars. And we look at frequencies from 1 to 10 gigahertz, 1,000 megahertz to 10,000 megahertz. Why there? Because it's where nature gives us a quiet window on the universe. Lower frequencies, there are a lot of electrons spinning around the magnetic fields of the Milky Way galaxy. They emit synchrotron radiation, and it gets stronger, noisier as you go to lower frequencies. And then we have an atmosphere that has water vapor and oxygen in it. So much above 10 gigahertz, we begin to get noise from that. Our quiet window on the natural universe is 1 to 10 gigahertz. That's where we're looking first in the microwave region. And we have very efficient algorithms for finding artifacts, for finding patterns in a two-dimensional plane. So this is frequency, and this is time. And our frequency channels are 1 hertz wide. Our time samples are 1 second long. So the frequency time plane is fully sampled here. And if I want to study 1 to 10 gigahertz, you can do the math. With 1 hertz channels, I had to look at 9 billion channels per star if I'm looking for narrowband signals. Why am I looking for narrowband signals? Because it's the kind of thing that our technology can produce, but as far as we know, nature never can. My colleagues that are looking for optical signals, they don't look for frequency compression, they look for time compression. They look for pulses that are a billionth, a nanosecond, or less long, because nature doesn't produce such pulses, but lasers do. So we're looking for evidence of technology. Now, I've talked in front of this slide a long time. Have you seen the signal? All right. Can you see it? Can you see me now? Can you hear me now? Okay, look. How about that? And that's a really strong signal to our algorithms because we coded them to find precisely that kind of thing. A narrowband straight line in the frequency time plane. But what if we're looking for the wrong thing? What if the pattern that's there to be detected is something for which we don't yet have an algorithm? Well, that's why in 2009, when I was given a prize by TED, my wish, so you get this prize, that's great, you also get to try and make a wish to change the world, and TED tries to make that wish come true. So I asked TED to empower Earthlings everywhere to become active participants in the ultimate search for cosmic company. So, starting now, all of you go in and change your Facebook pages and your Twitter profiles and your LinkedIn things, and add Earthling to your description. Add Earthling and think about what that means. Let's change some perspectives here. All right? So, I've got good algorithms for the kind of signals I know about. What about the kinds of signals we don't yet know are in the data? We want to build a citizen science project that allows people to use their brains, their eyes, and maybe even their ears to find patterns that we haven't programmed our computers to find, and to work in pieces of the spectrum where there are so many signals that it confuses our computers. We want people to get involved, right? We want your generation to get involved because you're the key to our longevity, right? So Alan Stern used to run the Space Sciences Division at NASA. He came by our place one day and he said to me, "Jill, you mean that all the people in the world that are actively working on SETI could fit in a phone booth. And yeah, when you think about the kind of phone booth stuffing we used to do, he's right. Well, what a shame. I mean, there are a heck of a lot more bright people out there in the world that could help with the search, and are motivated and think about SETI than just the few of us that do it professionally. So about a decade ago, right, SETI at Home came out of Berkeley, but we gave them the algorithms that we use on the telescope in real time, and they use them to process data that's recorded at radio telescopes, and they process them after the fact. And so they wanted you to do distributed computing, service computing, and that was a good start. But, you know, and when they're not looking at where they are on the leaderboard, the people involved in SETI at Home sometimes write haiku poems like this one. And what does this say? It says they're really not involved. They plugged their computer in, they installed the screensaver, and they walked away. They're not thinking about SETI. Not likely that we can change their perspective very much. We want active participation. So SETI at Home was a great start. It's a good idea, but how do we get the world actively involved so we can talk to them about what it means to be an Earthling? And that's what SETIQuest is all about. It's an attempt to build a global community that's actively engaged so that in the process of helping with the search, people have to think about the fact that they live not in San Jose, they live on the planet Earth, which is just one planet around one star in a big galaxy. They have to put thought into their cosmic situation. So we're trying to build this community. We start with the telescopes. We got some nice donation of enterprise servers. We have support from Amazon Web Services. So as a starting point, we're throwing a lot of our data every Friday afternoon. Instead of doing our signal processing in real time, we just record direct to disk and put it in the cloud. We have also published on GitHub our code that we've built over 2.5 decades. We've now open sourced it. We're saying, go take anything in there that's useful to you and use it, or help us make it better. We're trying to attract the digital signal processing community, particularly students in electrical engineering who are studying this sort of thing, to help us build better algorithms. Once we define what we want, let's build algorithms that don't just look for narrowband artifacts, but look for other kinds of information-bearing signals and distinguish them from noise. So we have 5 projects in the Google Summer of Code that were accepted this summer, and we're now looking at the student applicants, and we'll be starting with this community. We are also working on building this citizen science application. Uh-oh, darn. Sorry, it was supposed to, the screen was supposed to stay on because it was plugged in, but it didn't. All right, we have an application that we've developed for, I don't want to install something now, forget it, install later, that we call SETIQuest Explorer. And it works on Android devices, so it works on this nice tablet, it works on Android phones. We also have a browser version, and it will allow you, it's very early days, so go to explorer.setiquest.org and sign up to help us beta test this. It's our first attempt at letting people look at data and see what patterns they see in the data. It's running off stored data in the cloud. It's been done by Francis Potter and the Heather Saj group with a little funding from Adobe. And the next step is to start working with Galaxy Zoo. If you've not done citizen science, if you've not encountered Galaxy Zoo, go take a look. It's really fun. Lots of interesting projects that let you help do the science that scientists around the world are trying to do. We're going to work with them to make this a real-time detection. And it's It's very difficult. It's trying to solve a problem that Galaxy Zoo hasn't solved yet. It's getting the results from the crowd analyzed, weighed, and judged, and having those results go back to the telescope, right? Go back to the telescope within 4 minutes, so that if you discover an interesting pattern, we can go back and follow up on it in near real time, the way we do our normal signal detection. So closing that feedback loop in 4 minutes is going to be a huge challenge, and it's really fun to think about what else you could do with that if you can manage to solve this. So here's the Google Summer of Code. There's stored data on Amazon. You can download it, and what you will get presented with is this spectrum, right? Intensity versus frequency. We can actually record 8 megahertz of data direct to disk. This was recorded at 1420 megahertz. So that's hydrogen. That's a natural signal from the galaxy. But if you move your cursor along, you can get the 1 hertz look at this data. And if you notice that little bump right there, and you click on it, then you get these waterfall plots, the kind of thing I showed you before. Frequency versus time. And look, there's a really interesting signal there. But when our code detects it, when our algorithms detect it, they actually throw away all of the information in this frequency modulation, and they just say it's a broadband signal and it has a drift rate about like that. And so I can't distinguish this one from that one, and I think there's a lot of information in the frequency modulation that might help us figure out what source is producing this, and maybe then we can schedule around it. So one of the projects for the Summer of Code is helping us to better characterize those signals. And here we have the mobile application. Oh, come on. Which, right, it allows you to swipe, and once it loads up, look for patterns here and see what, and tell us, I see a pattern, and then tell us what kind of a pattern it is there. And my ID gets taken out of the database because when I do these demos, and there's no pattern there, but I just told it there was, it's skewing the statistics. So we exclude me from these data. But if you want to help beta test and strengthen this and give us ideas about how to make it better, please do explorer.SETIQuest.org. So we are really excited. Okay? Things are changing. We're changing the way we do our business. We're changing what we know. So we now know where to point our telescopes. And we have a plan to spend the next 2 years observing those Kepler worlds over 1 to 10 gigahertz and involving Earthlings in our search. Right? We're successfully building beta-type prototypes of tools, and we're working with Galaxy Zoo. And boy, is this a really cool time or what? It's a really cool time, guys. It's really neat. But, oops. Tomorrow, I will be hibernating that array because of the California state financial situation and the U.S. funding situation with the 2011 budget. We actually have lost, we don't have the funding for that 2-year program. So we're going to have to begin a private-public appeal once more. We went through this in '93. We're going to go through it again. And so it's the best of times. We have this all staged to do a terrific project for the next 2 years, but we don't have the funding, and we have to go out and raise it. And why bother? Right? Why? Maybe you're sitting there saying, why bother? Well, again, think about the Earth. Think about being an Earthling. For millennia, we've seen what happens when you take a small island of life and you cut it up into even smaller and smaller islands. In the end, in fact, we all belong to only one tribe, and that's the Earth. And we really owe it to ourselves to celebrate the commonalities of all people on this planet rather than fighting over our differences. So SETI has this amazing opportunity to hold up a mirror and show us ourselves from a perspective that we usually don't embrace. And as we do that, I think that we can help to trivialize the differences among humans. And so I'd like for all of you to join us in this search. Thanks for having me.
Dr. Tarter, last September, several retired U.S. Air Force officers told the National Press Club that they had documented 120 instances of nuclear missiles deactivating within minutes of UFO sightings above ground at the same installations. SETI scientists have referred to this as a potential candidate signal. Given that nobody has yet suggested that the retired officers are untrustworthy or have a reason to be untruthful, what is the current status of that candidate signal, and how would you propose responding to such a signal if confirmed?
Okay. I've actually suggested that those officers are not necessarily credible witnesses and trustworthy. So I don't necessarily believe the data that have been shown. If it's an EMP, if it's a big electromagnetic pulse that was set off, we certainly are not going to respond in kind. And in fact, we're not going to respond at all until there has been a lot more investigation into the credibility of that. And even if that were to be shown to be a credible signal, we're still not going to respond, because first we have to have a conversation with the planet about should we respond. Some people are very fearful about making our presence known. In fact, it's a bit too late. We've been leaking for a long time, but nevertheless, the world deserves a conversation, and if we decide to respond, how do we respond? Who will speak for Earth? What will they say? Conversation it's been very hard to have in the past, but I think all the social networking technologies that we have now will allow us to have that conversation. So, incredible claims, you know this, incredible claims demand incredible evidence, and that has not yet risen to the level of the bar that has to be actionable.
Regarding the measurements that Kepler itself takes, does it take into account any dark matter or black holes that might affect the measurements?
Okay. Kepler has not yet had to invoke anything exotic beyond Kepler's laws of motion to explain the transits that they've seen, right? And dark energy, dark matter tend to be more on a very large scale. So our galaxy is embedded in a halo of dark matter. On the scale of the solar system or a planetary system around one of those stars that Kepler's looking at, dark matter and dark energy just don't have that much sway. It's large scales where you see that come in. So we see the planets tugging on one another as well as tugging the star, but no dark energy required yet.
Last question.
For Kepler, how does it figure out if there's a galaxy sideways instead of just vertically onto it? What if there's a planet going in front of the sun over here that's coming this way, or you read that way?
Kepler actually can't find those. That's why it has to look at so many stars in order to find if the planet is rotating on the sky this way. It doesn't ever pass in front of its star, so the transit technique doesn't work. Astrometry would, actually trying to measure the centroid of the star as it gets tugged this way and then back that way. And an inclined orbit that actually has some component of its velocity vector towards you will allow you to use radial velocities to see the star tugged forward and back, even if that orbit isn't inclined enough to cause a transit. So not all planets around all stars will cause transits. That's why Kepler's looking at so many stars continuously.